Every time you stream a video, power your phone, or receive a text, invisible waves are racing through tiny highways made of metal and air. These highways are called transmission lines and waveguides. But how exactly do they work?
Everyone, my name is Azis, and in this video, we will dive into the concepts of physics behind transmission lines and waveguides. Let's go!
A transmission line is a structure that guides electrical energy or electromagnetic signals from one point to another, forming a path between a transmitter and a receiver in power or communication systems. To understand how a transmission line behaves, we can model it as a series of tiny segments, each with four key electrical properties: resistance, inductance, conductance, and capacitance. Resistance depends on the conductor's material and shape and increases with frequency due to the skin effect. Inductance comes from the magnetic field generated by the current and resists sudden changes in that current. Capacitance is due to the electric field between the two conductors, acting like a parallel plate capacitor. And conductance represents the small amount of current that leaks through the imperfect insulating material. These parameters represent how the line stores and loses energy as resistance and inductance appear in series, modeling the wire itself, while conductance and capacitance go in parallel, representing the insulating material between conductors. This repeated structure forms that we call the equivalent circuit of a transmission line, and it helps us understand how voltage and current waves move, reflect, and lose energy as they travel. When we talk about transmission lines, there are two key properties that really help us understand how signals behave as they travel: characteristic impedance and the propagation constant. These properties are easiest to study when the line is built evenly along its length, meaning it's uniform and symmetrical. That way, the signal moves smoothly without sudden changes or reflections, making analysis and design a lot more predictable. Firstly, characteristic impedance, often written as Z0, is the ratio of voltage to current for a wave traveling along a uniform transmission line without any reflection. In terms of parameters, characteristic impedance is represented as: in a lossless line, this is determined entirely by the inductance L and capacitance C per unit length, and is given by. Next is the propagation constant. It is defined as the ratio of current achieved at the output to the current applied at the input of the system. It is denoted by the Greek letter gamma, which describes how signals change as they travel along the line. It's a complex value made up of two parts. Here, alpha is the attenuation constant, also known as decay, representing how much the signal weakens per unit length, and beta is the phase constant, which tells us how the signal's phase shifts over distance. Together, therefore, these properties explain how electromagnetic waves move through a transmission line. Okay, when we talk about transmission lines, there are many types of transmission lines, but in this video, I'll be focusing specifically on waveguides. A waveguide is a specialized type of transmission line designed to confine and direct the propagation of electromagnetic waves, typically at high frequencies such as microwaves, infrared, or even visible light. Unlike traditional cables with central conductors, waveguides are usually hollow metallic tubes that guide waves through internal reflection along their walls, minimizing signal loss. Usually, they take in the form of rectangular or circular tubes.
Okay, so this might be an ordinary shuttlecock container, but it is actually a great way to understand how a waveguide works. So if I put my voice into it, you'll notice that it echoes slightly.
That's because the sound waves are bouncing along the inner walls as they travel. Waveguides do something similar, except instead of sound, they guide high-frequency electromagnetic waves like microwaves. The waves reflect inside the hollow metallic structure, following a defined path from one point to another. Inside a waveguide, electromagnetic waves don't just travel straight through like water in a pipe. Instead, they bounce off the walls and form specific patterns called modes. Each mode describes a unique arrangement of electric and magnetic fields across the waveguide's cross-section, but not all frequencies can form stable modes. The wave must be above a certain threshold, called the cut-off frequency, to actually propagate. Below this frequency, the energy just fades out instead of traveling. So the two main types of waveguide modes are transverse electric, also known as TE, and transverse magnetic, also known as TM. These modes describe how electric and magnetic fields are arranged as the wave propagates, usually in the Z direction or the direction along the waveguide's length. In TE modes, the electric field has no component in the Z direction, while the magnetic field does. In TM modes, it's the reverse. Both modes arise as solutions to Maxwell's equations with the boundary conditions of a hollow metallic waveguide. Did I mention earlier about the cutoff frequency? Well, it is the minimum frequency needed for that mode to propagate. Below this frequency, the wave doesn't bounce in a stable pattern and simply fades away. Also, if we compare TM with TE, TM modes have a higher cutoff frequency than TE for the same waveguide dimensions and mode indices. That is why TE10 is used as the dominant mode in rectangular waveguides, which brings us to the next part, application. The TE10 mode is the most common in rectangular waveguides and is known as the dominant mode. It's used extensively in radar systems because it provides efficient, low-loss transmission at high frequencies. In this mode, the electric field is transverse, and energy travels primarily along the length of the guide. The TM01 mode appears in circular waveguides and is often used in microwave heating or particle accelerators because this mode has a strong axial electric field. It's great for focusing energy towards the center of the guide. Each of these modes is used for a specific purpose, depending on the design of the waveguide and the frequency of the signal.
Here's a question for you. Are the power transmission lines that we see every day are actually waveguides? Well, the answer is no, and here is why.
As you may know, waveguides are designed to carry high-frequency waves like microwaves, where energy bounces off the inner walls in specific patterns. Power lines, on the other hand, carry low-frequency AC, usually 50 or 60 Hz, which is far below the cut-off frequency needed for waveguide behavior. Instead of bouncing waves, power lines transmit energy through conductors using transverse electromagnetic, also known as TEM mode, which means no internal reflection are involved. So while both do guide electromagnetic energy, they do it in completely different ways. One of the most familiar and important applications of transmission lines is in power transmission, which is the high voltage lines you see along roads and across the country. In these long-distance systems, all the transmission line parameters we've discussed, which are resistance, inductance, capacitance, and conductance, play a critical role. For example, high resistance leads to power loss, and the line's inductance and capacitance affect how voltage and current behave over long distances. Engineers use the concepts of characteristic impedance and the propagation constant to analyze how efficiently power is delivered, how much signal might reflect, and how much energy gets lost along the way. Another key aspect is voltage regulation, where the voltage at the receiving end can drop due to the line impedance, especially under heavy load. That's why impedance matching and proper line design are essential to keep the system stable and efficient across long distances. Besides power transmission, transmission lines are also used in various applications like radio frequency communication systems, antennas, radar, television, and even the internet. In conclusion, transmission lines come in many forms, and waveguides are one specialized type. Standard transmission lines like wires or coaxial cables carry low to mid-frequency signals, whereas waveguides are designed for high-frequency waves like microwaves and light. They all work on the same basic idea, which are guiding electromagnetic energy from one place to another. By understanding how signals behave in these structures through impedance, reflections, and wave modes, we get a clearer picture of how everything from power lines to radar system actually works.
Hope you guys enjoyed the video, and thanks for watching.